Okay, as discussed earlier, that we might need here to convert the binary floating point into its normal form. We call this process as normalization, and we have needs here to actually consider the normalization conversion here. Okay, one of the reasons here is precision of the value itself. Let's take an example here of what is going to happen if the number is not normalized or in normalized form. Okay, now let's consider the value of 2. Okay, so the mantissa here is represented by 0, the most significant bit, and then the binary point, and then here we have 1, and then the rest of zeros, and the exponent here is representing the value of 2, so it will be half multiplied by 2 to the power of 2, which is going to be 4. 4 divided by 2 equals 2. Okay, this is for number 1. Number 2, here we have a different representation in a binary floating point, where we have here the exponent as equal to 3, and the mantissa here is equal to a quarter actually, so quarter times 2 to the power of 3, which equals 8. 8 divided by 4 also equals 2. As you can see here in example 3, that also we have here mantissa value as this is half, this is quarter, this is eighth, and then the exponent equals 4, so it will be 1/8 times 2 to the power of 4, which is 16. 16 divided by 8, which is going to equal also 2. Example number 4, that this is a representation also for the mantissa, where it has a value of 2 half, quarter, eighth, 1/16, and the exponent is 1 to 4. The exponent is 2 to the power of 5. 4 plus 1 is 5. This is 32. 32 when divided by 16. This is going to be also 2. As you can see here, we have different representations of the ordinary value of 2 as different infinite number of representation of binary floating point. Actually, this is going to be considered like a waste of space for this example. Also here we have leading zeros here to the left. We are wasting the space of binary digits. Also here we have 2 zeros to the left. But here, as you can see, that the most significant bit is 0, which is representing positive value. And then we have here 1 after the most significant bit and after the binary point. And we call this form of binary floating point representation as normalized form. Okay, normalized form means that the first and the second values are different, whether they are 0 and 1 for positive values, as +2 here, and if they are negative values, so they must start with 1, and then the value of the binary digits after the most significant bit should be 0. So the normalized form should start 0, 1 or 1, 0. This is for positive values, and this is for negative values. As shown there are several ways of representing the number 2 using this sequence. If we kept shifting to the right, we end up having the value of 2 in binary. This could lead to problems. To overcome these issues, we use the method called normalization. Now, normalization example here, as you can see in front of you, the value of 0, 0, 0, 1, 1, 1, 0, 0, and then the value of exponent here is 0, 0, 0, 0, 0, 1, 0, 1. What's the value in binary? So simply what we're going to do here, shift the bits left to get the value to the form of normalized form. So we'll shift the binary point here, one space, one point, and then another digit. So we're shifting here by 2. So we will have this value, we'll get this value 0, 1, 1, 1, 0, 0, 0, 0. And then since the bits were shifted 2 places, okay, 2 places left, as you can see here, that the bits has shifted here to the left, so the binary point has 2 places here. So that means the exponent must be reduced by also 2 to give 1, 1. The exponent value here is 1, 2, 4. That means 5. We have to reduce this by 2. Okay, so this will give us 3. What's the value of 3? It's 1 plus 2. Okay, so the exponent should be changed from 0, 0, 0, 0, 0, 1, 0, 1 into this value because we have shifted the digit and we added the binary floating point here, 2 spaces. Actually, we removed the padding leading zeros, okay, to have the form of normalized form. Okay, this gives the 0, 1, 1, 1 as here, and the exponent will be also changed, which is now normalized. How to figure it's normalized? By the leading 2 digits should be different. Okay, let's take another example. Okay, as here, these values of mantissa and exponent. Okay, now to convert that into normalized form, obviously this is not a normalized form because you have here leading zeros, which also a waste of space, and we need to put the binary point to this place, to this position. Okay, that means we need to shift the binary digits 3 places to the left. So since this value is 1, 2, 4, this is 6. Okay, this is 6. So also here, as we did previously, we need to reduce the value of exponent by 3. Okay, so the value is 6, needs to be 6 minus 3 equals 3, and the number is going to be, this number is going to be 0, then 1, 1, 0, 1, and then you complete the rest of them, because 1, 2, 3, 4, 5, 6, 7, 8, we have 8, so also the same 1, 2, 3, 4, 5, 6, 7, 8, and the exponent here is 6, it's going to be 3, so it should be like this, 1, 1, okay, and then 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is in a normalized form right now, and the exponent has been reduced by also 2. Okay, try to practice with the rest of the examples here. Okay, guys, and let's also here consider that what could be the potential rounding errors and approximations by in the representation of the following example. Binary number 5.88 using an 8-bit mantissa and 8-bit exponent will lead to inevitable rounding error, since it is impossible to convert the binary number into the exact binary equivalent. Okay, if you try to convert that 5.88 into equivalent binary, okay, you will have definitely a rounding error because you will keep rounding ones and 0, 1, 0, 1, 0, and until the space or the number of places reserved for the mantissa is fully occupied. It will not find any other space. So this is causing like a rounding error, and this error could be reduced by increasing the size of the mantissa. So let's say, for example, if we have 8 spaces, 8 positions for the mantissa. Okay, to reduce this error, okay, for sure we can reduce the rounding error by increasing this to 12 bits or 16 bits, for example. Okay, a 16-bit mantissa would allow the number 5.88 to be represented as 5.875, which is definitely a better approximation. So in complex calculations, if we are using like hundreds of different um, numbers and multiplied, division, subtraction, and so on, and you have this approximation to from 3 places to only 2 places, definitely this is going to produce also an potential rounding error and approximation. Also, we will consider now to represent the denary number 5.88 using an 8-bit mantissa and 8-bit exponent. To convert this into binary, we will use a method similar to that used in the previous explanations. Okay, so simply you are going to multiply the decimal value by 2. Do you remember that when we used to convert from denary to binary? Okay, when we have whole numbers, for example, the value of 17, we keep successive division. 17 divided by 2, which is going to be 8, and the remainder 1. And here divided by 2, this is going to give us 4, and the remainder 0. Divided by 2, 2 remainder 0. Divided by 2, it's 1, and the remainder is 0. And then here the remainder will be also divided by 2. This will equal to 1. So the value is 10001. Okay, the same thing here, but we are going to do the opposite since we have fractions here. Okay, we will first consider that we need to calculate here that this approximation is correct or not. Okay, so 0.88 times 2, this will be 1.75. So we will use the 1. We'll consider the whole number here. Okay, 1. And the value here after the decimal point will be multiplied again by 2. This will give us again 1. And then 52 will be multiplied again by 2. This will give us 1.05. Also, we'll consider only the 1. And 0.4 will be multiplied by 2. This will give you 0.8, and the value should be considered as 0. As you can see here, 1, and then 1, 1, and then 1, 1, 1, and then 1, 1, 1, 0. Okay, then 0 to 0.8 is going to be multiplied by 2, which is 0.16. So we will now use the value of 0 since this is a 0 here, and then the binary value will be 1, 1, 1, 0, 0, and then so on. Okay, as here until you reach to 0.64 times 2. This is 1.28, and as you can see here, 1 appears for us again here. Okay, at the end, and as you can see, also the value started to increase again. And this will give the value, this final value, which has 1, 2, 3, 4, 5, 6, 7, 8, 9. We have to stop here since our system uses a maximum of 8 bits. Now the value of 5 in binary is 0101. This gives this value 0101, and then 111, and then the rest 00001, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is represented in 12 positions. If you keep repeating, the value will start to give you different values later on. Here might be 0, and then 1, 0, 1, 0, 1. It will be start repeating, and as soon as you have more positions for the mantissa, the value will be more accurate. We have to stop here since our system uses a maximum of 8 bits. Now the value of 5 in binary is 0101. This gives this value. Moving the binary point as far to the left as possible gives this value times 2 to the power of 3. 2 to the power of 3 since the binary point was moved 3 places. Okay, so 5.88 is stored as 5.75 in our floating point system because we are only required a maximum of 8 bits. Okay, so we don't have much spaces here or positions to store the binary points. Okay, that's all for now. I wish that you understood this topic of floating point rounding errors and approximation, and also the how to normalize the floating point.